In 1820, Hans Christian Ørsted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current. This was a rich scientific discovery, but until Ampère could work out the consequences of Ørsted's experiment, it would remain little more than a single piece of a complex puzzle.
I'll do my right face, and I start marching until I get past the object. I'm counting the steps from where I made my last facing movement up to this point here.
So, like anyone starting out in a new field, Ampère advanced one step at a time, armed with Ørsted's discovery.
I took 3 steps this way. I'm going to do the complete opposite, take 3 steps this way. Once I get here, then I do another facing movement, and I'm off. Shoot my azimuth again, and there you go.
But these Americans have at least one advantage that Ampère lacked. Instead of working in these quiet, peacetime surroundings, Monsieur Ampère began his scientific career in the bloody pandemonium of the French Revolution. Ampère's father, Jean-Jacques, was a justice of the peace who was labeled an enemy of the revolution. As he approached the guillotine, Ampère Sr. scribbled a final note to his wife. I do not leave you rich or even in common comfort, but my greatest expense has been the purchase of books and mathematical instruments, which were indispensable to our son's education. But this expense was in itself a wise economy. Considering what his son mastered, the elder Ampère's money was well spent indeed. At the height of his academic career, Ampère was known as a natural philosopher, wise in the ways of science and how it could explain some of the more fascinating mysteries of the universe. Today, Ampère is best remembered for his work in electricity and magnetism. And that work started with the fact that electric current flowing through a long straight wire produces a magnetic field that circulates around the wire. But how does the strength of the field depend on the distance from the wire? If a tiny segment of electric current could exist, it would produce a magnetic field proportional to the inverse square of the distance. The direction of the field is related to the direction of the current by the right-hand rule, or the vector cross product. The field would be biggest when the current segment and distance vector are perpendicular. But electric currents can never exist in tiny segments. So any real magnetic field must be found by adding up or integrating the contributions due to each segment of a flowing current. The field, due to current flowing in a long straight wire, is always perpendicular to the wire and decreases as the inverse first power of the distance from the wire. The net result is a field that goes in circles. The lines of force are circles concentric with the wire, and the field is the same all the way around each circle. On the other hand, if the wire is bent around into a loop, the current flowing through it produces what is known as a dipole field. A helical winding, or solenoid, is like a stack of current loops. It creates a field much like that of a bar magnet. If the solenoid is bent around into a circle, the donut it forms is called a toroid. The magnetic field of a toroid is contained completely inside the windings. There are no field lines outside at all.